So I have all kinds of homework to return to you. Can we do that at the end of the lecture? I have homework 8 has finally been graded. Here it is. Homework 9 is here for some people who didn't pick it up yet. And I'll keep these in my office, I guess. Or maybe, actually, I'll give them back to Isabel or Alex if you want to pick them up if you forget. All right, so yes. If you haven't gotten a homework that you should have gotten, the TAs have it. So there are 2 of them, and I don't know which one is the keeper of the homework. But they're in the same place. They're in 657 Rhodes. So yeah, go or send them an email about how you can get your homework back. Hi. Okay, so at the end we'll finish off with the homework. All right. Well, it's our last lecture. It's so sad, but I'm kind of excited to give this lecture, so I hope you'll have fun with it too. It's about work by some people that I know. Actually, one of them I taught in this class 20 years ago or so. And it's about a theme that we haven't discussed at all so far this semester, which is what is any of this good for in a practical sense? How could you use chaos to do something helpful in engineering or some other technological application? And so our theme today is using chaos, specifically something also that we haven't talked about, synchronized chaos. How you could use that for private communications. I don't want to say secure communications, like this is not as good as encryption, but it's an interesting idea, and it may have some potential for the future. Anyway, so you'll see what I mean as we get into it. Also, this is part of I guess you could think of it as a trend in the subject. That is, the early days of chaos theory were really just about the math and science of chaos as it occurs in nature. But now people are looking at it in engineering as a source of new devices, new thoughts, new technologies. So this is one of the earliest attempts in that direction. You can read about it in section 9.6. That's at the end of the Lorenz chapter. And so the work begins with Pecora and Tom Carroll, who wrote a paper in 1990. In which the idea of synchronized chaos was introduced. So Pecora worked at the Naval Research Lab outside of Washington, and he's a physicist, but I think he was feeling some heat maybe from his bosses that if you're going to study chaos, show some military use for it. If you're going to work for the Navy, is there something we could do with this besides just letting you have fun studying it? And so he's tried to think about what could you do with a chaotic signal. That is, once you phrase it that way as a signal, now you're starting to think about communications. And for any kind of communication system, you have to have a transmitter and a receiver, and they have to be in sync. So that immediately raised the question, if you're going to think of a time series from a chaotic system as a signal, or possibly a carrier of a signal, like a sine wave would be in AM or FM, could a chaotic signal be an interesting new class of carriers? Or could it also be used in some other way? And so these are the kind of questions that they were asking themselves, and they figured whatever we're going to do, first we have to figure out how to synchronize 2 chaotic systems, because that's the basis of all communications. And so right away that raises what was seen to be, at first, seemed like insurmountable problems, which is, we have sensitive dependence on initial conditions in chaotic systems. So you might think they can't possibly synchronize. And actually, a lot of people think that when they first hear this notion. It sounds like a contradiction. Chaos means 2 things will not be synchronizable, because any little difference or error between them will grow exponentially fast. And so how could you possibly synchronize 2 chaotic systems? But that's actually just wrong thinking. It is possible. And the point is that you don't have to make the systems, systems can be chaotic yet synchronized, because the important thing is the difference between them. If the difference dynamics are not chaotic, that is, like if the difference converges to 0, the systems can be in sync yet both be separately chaotic. So they were able to construct a system where that was the case, that it had two separately, I mean, they're coupled, that's the point, they're not independent. And so anyway, they actually considered, they built some circuits, they also did some math, but let me illustrate their idea using the Lorenz system rather than talk about their circuit. So in this framework, think about, well, here's the Lorenz equations. X dot is sigma y minus x. Y dot is Rx minus y minus xz. And z dot is xy minus bz. So that's our usual Lorenz system, and we're going to think of that as a drive. I don't want to say transmitter yet, because it's not actually going to transmit anything. Just think of it as a drive system and then another system that's going to respond to that drive and hopefully get in sync with the drive. Now, for the drive, for the response system, they chose this way of doing things. They said, let's suppose that R, so R for response, let's suppose that X in the response system is just identically the same function of time as X in the driver. It's as if you just sort of sent X of t over there into the response system, and it's going to use that as its X. But the Y and Z of the response system are not just that. They're going to obey differential equations of this type. R X of t minus Y sub R minus X of t, maybe I should call this X of t, times Z sub R. So you'll notice what I've done is I'm just writing the Lorenz system, except that where here I would have YR dot, you might expect this to say X sub R. I'm not going to say X sub R because I've replaced X sub R with X. But otherwise, it just looks like a Lorenz system. And similarly, the Z equation for the response system will be ZR dot is X of t, Y sub R, minus B, Z sub R. All right, now, so as I say, we're going to think of this as the response, and this one as the drive. Now also, you might notice that I've used the same R as the R over there and the same B. So we're going to assume that the parameters, like if you think of these as physical devices, that there's a system here that's generating some voltage or sound or something. These devices have identical parameters. The R sigma and B will be matched. In reality, that will never be possible, but for now, let's just suppose that they're identical. So assume matched parameters are sigma and B. Okay, now what they found in computer experiments was that with this setup, the response YR of t, notice, which is obeying these differential equations. Actually, maybe let me put it this way, just to clarify what's going on here. Here we have this system just minding its own business, generating Lorenz dynamics. It's producing an output, X of t, which is being fed into this system. And you've basically hijacked the X here and replaced it by the X coming from the drive. Meanwhile, though, this system has its own YR and ZR. And you know, like if you imagine these as having some kind of intelligence, the YR and ZR are part of a Lorenz system. They're expecting to see their own X, but they don't. They see X coming from this system. And what will they do in response to that? Well, they're going to end up, this YR and this ZR will end up becoming the same as the Y and the Z from the driver. This is what we mean by synchronization. That Pecora and Carroll found that even though they only sent over X information, that was enough for this response system to recreate the Y and Z information. Right? You get that that's kind of cool. You've only sent over a third of the information, yet all of it is being reconstructed. Not so obvious that that would be possible, but it does happen. And actually, even though I say as t goes to infinity, in fact, it happens very quickly, like on the order of, milliseconds, if you were running a circuit. So it gets in sync very fast. We'll see in a video that I brought how this works later on and how fast it really is. Okay, so is there any questions so far? Yes? In a physical system, would this be, did you say, immune to noise? Well, that's one of the questions that we're going to have to look at. How resistant to noise is this? Because, as you say, in a real system, there's going to be noise. There's also going to be parameter mismatch and all kinds of other complications. And like if you're sending a real signal through the air, there's going to be distortion of the signal, even if you send it down a wire or a cable. So there's a lot to think about. And later, you'll get to see, the short answer is that this system does work well, as long as the parameters are close enough. But it works surprisingly well. Okay. And is there another question? All right. So, by the way, I'm going to explain why this is true, and actually give a little proof that it's true. But you might ask, well, what was special about X? Why did I send over X? What would happen if I sent over Y or Z instead? Pecora and Carroll showed that this approach did not work. If you, instead of using X, if you use Z. That is, if ZR is replaced by Z of t. So it's a little bit mysterious about, like, why did the X work but not the Z? And in their paper, Pecora and Carroll gave some arguments about why this was happening, but it seemed to me that they weren't totally convincing arguments. They were a little bit loose. I think they're probably right, but a much cleaner and simpler and also more standard argument was given 2 years later that I want to show you now because it's so easy. Yes? What about Y? I don't remember what the story was if you did it with Y. I can't remember, but you could try it yourself. I don't actually remember. So, all right, anyway, simple proof that this synchronization in the sense described does happen with X as the driver. This was found by authors He and Vaidya, published in 1992. And it's sort of what you would first think of doing. That is, just look at the difference dynamics. So let's define E sub x, like think of it as an error signal, to be x minus xr, EY, y minus yr, and EZ is z minus zr. And think of these as functions of time. So E for error. Now, we know that there's no error in E, x, because it was defined that way. So EX is identically 0. X was chosen to be equal to, or XR is made equal to X somehow. But the others are not as obvious. EY, all we can say is it satisfies a differential equation, which you can get by subtracting this differential equation for YR dot from the equation for Y dot. So we have Y dot minus YR dot. And then let's see what happens. So we get minus y minus yr. By the way, notice the first terms cancel exactly. Rx cancels with this Rx. But then you have y minus yr and minus x of t z minus zr. I'm writing x of t. You may wonder, why am I saying x of t but not y of t and z of t? I kind of think of x of t as almost like an external drive. From the point of view of the response system, there's just this function, some weird function x of t coming at it. And so it looks like an external drive as far as the response system is concerned. Anyway, Ez dot would be, oh, actually, why don't we clean this up, the Ey dot, because you'll notice that this expression right here is just Ey, and this is Ez. And so this becomes minus Ey minus x of t Ez. Meanwhile, the Ez dot equation, by the same kind of calculation, gives us x of t y minus yr minus b z minus zr, which boils down to x of t e sub y minus b e sub z. Okay. And so we're left with this nice little system. Maybe I'll just write the dots over here again so I could put a box around it. Here's Ey dot, here's Ez dot. Okay, so stare at that. That's the difference dynamics. And what's going on with it? Well, first of all, it's linear in the variables Ey and Ez, right? They only appear to the first power. On the other hand, it's not autonomous. It has x of t in there, a possibly chaotic coefficient. So it's a second order linear system with non-constant coefficients. And it's not completely obvious what this thing will do. You can't just, for instance, look at the Jacobian and hope to get any information from that because it doesn't have constant coefficients. So you need to do something more clever. What we're trying to do here is show that Ey and Ez go to 0. And it might remind you of a calculation you once did. Does it remind you of anything? There's a homework problem that you did that had this flavor. Theoretically, that you did. Okay, it has to do with the Lorenz system. Really? Not coming back to you? Yes? Something with the Fourier series showing that, remember n, that was that the higher modes decayed in that, there was a one question. And so it was had a very similar flavor to this, that calculation we did with the water wheel problem to show that the higher modes decayed to 0. The same trick that you did there will work here. That is, what makes this difficult is these x of t's. And so if I could cancel out the x of t between the two equations, that would be good. Now, how could we do that? Well, what if I multiply this equation by Ey and this equation by Ez and then add them? Right? Then the chaos would cancel out. So Ey dot Ey plus Ez dot Ez. Well, what do I get? Minus Ey squared minus x Ey Ez from the first term, and then plus x Ey Ez. So those are the ones that are going to cancel out. And then plus, no, minus b EZ squared. So cancel this with that, and we're left with minus EY squared minus B EZ squared. Meanwhile, notice that the left-hand side is an exact differential. That is, this is d dt of 1/2 EY squared plus EZ squared. So that is all set up. That's we've just discovered a Liapunov function. That is, this expression right here, think of defining a function v that's 1/2 EY squared plus EZ squared. That function is what? Positive definite, because v is only 0 when both of these are 0, and otherwise it's positive. And v is, well, v dot is negative definite, because it's negative a sum of squares and the b is positive, right? So v dot is strictly less than 0, you know, except when we're at the origin. That is where EY and EZ are both 0. So anyway, we have here exactly, and v is smooth and all that. So these are the conditions that you need in the Liapunov theory to say that v of t is just going monotonically to 0 as time goes to infinity. And since v is the sum of squares, that implies that EY and EZ go to 0, which is what we wanted to prove. That proves that the system synchronizes. So as you see, it's a nice, easy little calculation. And so this is what these authors published, and that cleared up why this X drive actually led to synchrony, as Pecora and Carroll found. Is there any question about the reasoning? Okay, so this doesn't show anything about communications per se, other than that if you could build these Lorenz drive and response systems with matched parameters, they would be able to synchronize their chaos, which is kind of fun to think about what that would look like. Like if you've seen modern dance, I don't want to disparage any form of art, but you know, sometimes the motions look a little bit unpredictable of the modern dancers, and yet they could all be in sync. So if you want a picture of what synchronized chaos might look like, you could picture two dancers flailing around, except in exactly the same way. Or if you just want something more mathematical, you could imagine looking at the Lorenz system going around on its strange attractor, and if you had two copies of it, they'd be going in a synchronized dance eventually. Okay, so that's the early work. Now, let me get into what Kevin Cuomo did, Cuomo and Oppenheim, who figured out how to use these ideas for sending secret messages for private communications. So Kevin was a student in this course a long time ago. I'm not sure what he's doing now. I think he works for Lincoln Labs outside of Boston. At least that's what he was doing the last time I was aware of him. But so yeah, when he was a student, he was notable to me for a couple of reasons. His homework was always very nice and clean, and he wrote with very small, accurate printing that looked sort of typed, but it was with pencil. And I have a little theory about this that is not empirically demonstrated. It's just a theory. I mean, like a theory in the loose sense. That what can you tell about a student from his or her handwriting? Well, if a student writes sloppy, I have found that tells you nothing. That person could be a sloppy thinker or could be brilliant or anything in between. There's no information from sloppy handwriting. However, a student who writes like a little machine, that is usually a good student. So that's predictive, and not 100%, but it was certainly true in the case of Kevin Cuomo. He was very good. And he also, before the final exam, which I didn't do a take-home final that year, I had an in-class final, but I told students they could bring 1 page of notes, double-sided, 8.5 by 11. And so he was in his element with his little machine printing, and he wrote the whole course on 2 sides, you know, of this one piece of paper, and he made a point of showing it to me, and it really was very beautiful. So anyway, that was Kevin. Now, but he, for his thesis work, did this problem that we're going to discuss. I mean, among many other things. So how to use these ideas for private communications. And so the work is Cuomo and Oppenheim, published in 1993. Those of you who are electrical engineers will know the name Oppenheim, maybe, because he wrote a book called Signals and Systems. That's a pretty standard book. Al Oppenheim was Kevin's advisor. This was at MIT. And so the notable things in their work, and, you know, I mean, they did both do a lot, but Al was the advisor. So Kevin really did a lot of the hard work. He's the student. Anyway, he first of all built the first ever Lorenz circuit. That is a little analog circuit that runs, effectively implements the Lorenz system. Its voltages go up and down according to the Lorenz equations. This surprised me at the time, that it seemed like, why is it so hard to build a circuit? But of course I don't know about those things, so I don't appreciate that. And Kevin said it was hard, and that's why people hadn't done it. And that he said there's a very wide dynamic range of the solutions, x, y, and z of t, and it just makes it tough to get all the components to, you know, stay within their correct operating ranges and not saturate or act weird. So I don't know, but whatever. He, you can see his circuit. It's in my book, the circuit diagram, built out of resistors, capacitors, just off-the-shelf components, nothing fancy needed, just ingenuity. Multiplier chips to do the nonlinear terms like x, z, and that sort of thing. Op amps. Okay, so anyway, that was one contribution. Now, he also built another one of them, a copy. And so he's going to use one of these as a driver and one as a responder, or really, for communications, it's a transmitter and a receiver. And he showed, as you'll see in the video, that he could get them to sync. Could get them to synchronize their chaos. And so this answers the comment that was raised earlier that, you know, does this really work in real systems where there's noise and parameter deviations? They're not identical, even though they're designed to be close. It still works. Now, his synchronization scheme was a little bit different from Pecora and Carroll for reasons that you'll see were needed in if you want to send a message, not just synchronize chaos. So here's the slightly different dynamics that they used, Cuomo and Oppenheim. Same old Lorenz system. X dot is sigma y minus x, y dot rx minus y minus xz, and z dot is xy minus bz. But the receiver, instead of just sending over the x to be the x of the receiver, here the receiver is going to obey a differential equation. Xr dot is sigma yr minus xr. And so that is a different equation from the Pecora and Carroll scheme. But the remaining equations are the same. Yr dot is our x of t. That is, we now are plugging in the x from the transmitter right here into the place where you'd expect x sub r. It's just going to be x minus yr minus x of t z sub r, and zr dot is x of t yr minus bzr. So what Kevin first showed is that if you don't send any message, just use this, then this will synchronize in the sense that the error dynamics goes to 0. The error signal goes to 0. You can show that the vector E defined as E sub x, E sub y, E sub z, that goes to 0. And to do it, you use a Liapunov function v equals 1/2 1 over sigma ex squared plus ey squared plus ez squared. So it looks a lot like the He and Vaidya Liapunov function, except it's got this first term, 1 over sigma ex squared. I won't verify that it is a Liapunov function, but it's just the same kind of argument that we did earlier. And it's in the textbook if you want to look at it. By the way, so Cuomo did this independently of He and Vaidya. He didn't know about their work, and he was very disappointed, in fact, when their paper was published, because he thought he had found the first proof of synchronization. But it turned out he got scooped slightly. But that wasn't his main thing. Anyway, but he did, just for the record, he did have it be, he was working on it while they were working on theirs. All right, now we get to the good part, which is how do you use this to send private messages? Maybe I'll take questions before I get into that, though. Do you want to ask anything up till this point? Okay, I'm careful with the word private because Al Oppenheim taught me to be. You might be more familiar with the word secure. They always talk about secure communications. And he said, you must never call this secure. Don't say this is secure. Don't exaggerate, because secure really means something to people who know about communications. Secure means that if someone from the CIA comes and kills you and takes your device and brings the device back to the lab, they still can't break your code. That's secure. That's what you're looking for. Okay, that's because that's what happens in the real world, that spies come and take devices and try to break codes. Otherwise, it's not secure. Now, still, if you're just talking about like some kid driving around the neighborhood who's trying to listen in on your wireless, you can defeat that with something that's not militarily strength secure. You can defeat that with just, decent encryption. So that kind of thing is not totally secure, but it might be. There's degrees of security, but then in that case we call it privacy. Okay, so privacy means it's enough to defeat a not very motivated eavesdropper. But secure can beat anybody. So anyway, this stuff is certainly not secure, but it might be private. Also, around this time, there were interesting things happening. These were the very early days of cell phones, the early 90s. And you wouldn't remember this because you were just, little children at that point. But Princess Diana, who was then still alive, used to have boyfriends who weren't Prince Charles. And sometimes she would talk to them on cell phone, and her cell phone conversations were intercepted by the London press, the tabloid press that was interested in what she was up to. And also Prince Charles was meanwhile carrying on with his now wife, Camilla Parker Bowles, and both of them got caught saying sweet nothings to their lovers by the press because of a failure of privacy in cell phones at that time. And anyway, so people were very much interested in these questions of private communications back then. Anyway, okay, so now how do you use these ideas for privacy? Well, since I'm talking about pop culture, let me say a little more about that. There's a very good movie that I want to recommend, which is also old, and you may not have seen it, called The Conversation. Do we have any movie buffs here? Anyone know this? Yes, do you know the movie? Francis Ford Coppola, right? Yes, that's the one. Yes. So The Conversation is a classic 1970s movie. When Coppola was, who made The Godfather, was at the peak of his powers. And it's a movie about, Gene Hackman plays a surveillance expert. And his job, he's been hired by someone to listen in on a couple that are suspected of planning something. We're not really sure what they're planning, but we want to know what they're talking about. And so the couple, who doesn't want to be overheard, goes, I think it takes place maybe in San Francisco, I forget. But anyway, they go out in some public, very public place where there's loud music being played, street musicians, and they're like sort of in a carnival atmosphere, and they're whispering to each other about their, whatever it is they're planning. And meanwhile, Gene Hackman is far away with his special microphone, aimed at them, trying to pick up what they're saying. And so most of the movie is about him trying to filter out the sounds of all the loud drumming and music and hear their conversation. And so this strategy that the couple uses, turns out not successfully, but you'll see if you see the movie, is what's called signal masking. They're trying to mask their conversation by the loud sounds of the music and the surrounding street noise. And so that's one of the ideas that Cuomo and Oppenheim use, is signal masking. The chaos is going to play the role of the mask, like the loud sounds of the street. And the message is going to be the little whisper underneath the much louder mask. And so why it's relatively private is it's not easy to filter out the loud noise, to uncover what the message is underneath. So you'll see that's one of their techniques. But first, how do we think about this? There's another method, actually. Oh, actually, maybe I should say one other thing. Aside from this little proof that it works in the math, as I say, Cuomo had these real circuits, and you'll see him in a few minutes on the video demonstrating how they work. But one test that they use is to look on an oscilloscope at the signals coming from both the drive or the transmitter and the receiver. And a standard picture is to graph, let's say, x versus x sub r. Because if they're the same, then you'd expect the signals to, although they're moving in time, they should lie along the line, the 45-degree line, where x equals xr. So you'll see in some of these movies that there's this, on the oscilloscope, the system is running around back and forth, but always staying pretty close to that line, indicating that the synchronization is pretty good. You can also look at the other channels to see that the same thing is happening with y and y sub r. So that's the kind of thing that will happen, and it's quite stable. It will stay on that line for as long as you watch. The system itself runs at kilohertz frequencies. At least this is what was true back in the original days. These things have been improved quite a bit in the 20 years since then, but back then it was running at kilohertz. And as I mentioned earlier, without coupling between the systems, their chaos would cause them to decorrelate because of sensitive dependence on initial conditions. Without coupling, they would decorrelate in about a millisecond. Decorrelate meaning lose synchronization and just run totally independently. Around 1 millisecond. So earlier in the course, when we talked about the prediction horizon for chaotic systems, or the Liapunov time, that's what I'm saying, that these circuits have Liapunov times of about millisecond time scale. Okay, now, how to send any kind of message? Well, sometimes you'd be interested in sending binary messages, you know, like in computers, data, and sometimes you'd be interested in sending human speech, which would be more like analog, although you could digitize it. But they had methods for both kinds of masking or communications, private communication. So if you want to send a bit stream with this technique, one way you could do it is to use parameter modulation. That is, think about it this way. Here's just a quick example. Suppose we think about the parameter b, that, remember, is supposed to be identical between the two systems, between the response and the drive. So they're supposedly at the same b, and so if you change the b in the driver, in the transmitter, to be a function of time, where you think of it as looking like this, that here's the standard value, but then you make it go up to something else, and then, you know, you might have a long period like that, and then you make it again go up. If you send something like this, so this is the old, that is to say, the agreed upon value that you and the receiver both have. By the way, you should keep in mind, like, if you really imagine this with a sender and a receiver, they have to agree on this day what are sigma and b to use. That would be sort of the method, right? That is, I'm going to send you something. I want it to be private. You can't understand what I'm sending unless we have matched our devices. So we have to agree what our R sigma and B are today. And of course, if that's stolen, then, you know, by the National Security Agency, then your system's not going to be private at all. But assuming that you can keep that part secret, then you don't know what message is being sent, but you'll still be able to decode it as long as you have the parameter values. So this is the old value of B, and then this is some other value, let's say B plus epsilon. Now, if you use that in the transmitter, then you send x of t to the receiver in the way that we described. And you just broadcast that. That's just going out into the air, or over a wire or whatever. And so the x of t is potentially public. Anyone could eavesdrop on that. But you have not broadcast the b of t. That's being held just in your device. And so what would happen is, suppose someone intercepts the x of t. So if x of t is intercepted by an eavesdropper, well, it's going to look like Lorenz chaos. That is, it will look like, you know, x as a function of time is whatever, some, you know, I don't know, something like this, and then, you know, whatever. It's just going to be some nasty thing. And hopefully, well, also you could try listening to it. That is, if you use it to drive a loudspeaker, amplify it and use it to drive a loudspeaker, it will sound like a hiss. It sounds like noise. Or like static on a radio station that's not picking up any, sorry, on a radio that's in between stations. It would just sound like garbage. Meanwhile, though, the information about B of t is buried in there. And so how does that get extracted by the receiver? Well, think about what the error signal would look like at the receiver. Suppose that at the receiver we look at E sub x, which, remember, is defined as x minus xr. Now, this is where the importance of the Cuomo and Oppenheim approach becomes clear. So remember, they've changed the first equation up there. Their XR dot is not what it was for Pecora and Carroll. Pecora and Carroll just had XR equals X. So at this point, Pecora and Carroll's approach would just produce identically zero error. That wouldn't be informative. Whereas Cuomo and Oppenheim, if they graph E sub x as a function of time at the receiver, and of course the receiver has both x and its own reconstructed version of x that's called x sub r, it would see, I mean, can you imagine what it would see? During this part, when you're using the standard agreed upon B, there would be basically no error, because you're using the B that they're, you know, I mean, you'd have synchronization. So there would be no error, or maybe a little noise, but basically nothing. However, when you use the different B, then the transmitter and the receiver are using different parameters, so they won't synchronize, assuming they're substantially different. And so you'll now see a substantial error signal. But then as soon as the value is restored to its standard value, within a millisecond, you resynchronize, and then you have this, and it'll stay like that until the next time that it's flipped, and then it will look like that again until the next time it's reestablished. And so this is what the error signal will look like at the receiver, and you can imagine that it's easy to reconstruct, but with a little bit of filtering, that this is the attempt to send a 0 and a 1, and then a bunch of zeros, and then a 1, and so on. Okay, so that's at least one way of trying to send a bit stream. That's how you would recover it. Is there any question about the strategy there? Yes?
There's like the 1 millisecond time scale.
Yes.
That would be too long.
Well, yes. Okay, you couldn't send very interesting. Right, so you're not sending, you're saying because we have to have this up for times that are fairly long compared to a millisecond. So the data transmission rate is going to be lousy. Yes. Now, since then, people have figured out how to do it on fiber optic cables. They're not using electronics. I mean, this was just, as I say, like Radio Shack level electronics. But you can do it with much better, like using lasers, optical communications instead of these little off-the-shelf hardware. And so people have since found ways to communicate at much faster bit rates. But at the time, this was like a proof of principle. But you're right, this wouldn't be practical for anything back then. Is there another comment or any question? Okay, so now for the part that I think you'll get a kick out of, which is how to send speech. And the video runs about 8 minutes, so let me just get through this, and then we'll finish with that video. All right, so to send speech, we're going to use the idea that I mentioned in connection with the movie, The Conversation. So analog signals. We're going to use signal masking. Which is not the fanciest method, but it'll make the point that we're going to let S be the signal that we send over the channel. And it's going to have two parts. It's going to have X of t, which is the chaotic mask, plus M of t, which is the desired speech or message that's being sent. So the X of t is the analog of the street musicians and the sounds of the water fountains and other stuff in the movie, and then M of t is the message. And in order for this to have good coverage, good masking, you want the mask to be much louder. That is, it should be much bigger in magnitude than M. Now, what you do then is in the receiver, so rather than sending X as we did at the beginning, that is, we used X to go out into the air and then drive the receiver. Now we're going to use this combined hybrid here, x plus m, and we're going to broadcast that. So that is, we're now going to use the dynamics over at the receiver to be xr dot sigma yr minus xr. Yr dot will be r times s of t. That is, where this used to say x, it's now going to say s of t minus yr minus s of t zr. And finally, the zr dot would be, again, you send s of t y sub r minus b z sub r. Then, so that's been sent over. Now, what do you think is going to happen? You've sent over this thing, which you can think of as, it's a little bit weird to think of it this way, but this is, in a way, natural for this problem. Think of x as being slightly corrupted by the message. Usually you think of a message corrupted by noise. Here I'm going to take the point of view that x, being Lorentzian chaos, is sort of what it's supposed to be, but then it's getting a little bit messed up because someone's put a message inside of it, or on top of it. When that x plus m gets over to the receiver, we already know that if you sent pure Lorenz chaos, this would regenerate xr, would be a perfect copy of x. So the thinking is, when you send over s, we're hoping that x at the receiver will be approximately the x, the Lorentzian chaos that's the mask. Because sort of the message doesn't make any sense from a Lorenz dynamics point of view as far as the receiver. So if the receiver just regenerates the xr, then you're in business, because then you can estimate the message as m hat equals the s that was sent across, which, remember, is going to be basically the sound of street music, minus the thing that you recovered over here, which is sort of like street music without the message in it. And anyway, if you add this up, then we're going to get what? So s is x plus m minus xr. And so to the extent that x and xr are equal, then this is your estimate of the message, right? I mean, you're hoping that this is approximately m. And so that's the question. How well is this going to work? And so that's what I want to now play for you. Kevin will explain how it goes. Incidentally, when you listen to it, first he's going to demonstrate that the circuits really do synchronize. Then he's going to, that is when there's no message. Then he will use a message which was very much of his era, which was a Mariah Carey song. Although I see she's back. But 20 years ago she was very popular. And so she had a song called Emotions. And you'll hear her singing Emotions. Oh, you're nodding. Maybe you like Mariah Carey. One student, the 1 year at that time, asked, is that the signal or the noise? Different taste in music. But anyway, so you get to hear Mariah after the chaos is stripped off. OK, let's see if I can get this to work. So we got to go dark. And laptop. Yeah, I didn't really get my timing right here. I hope I have some projection. Is it going? Okay.
I'm here with Kevin Cuomo. to look at a demonstration of using synchronized payoff for Coppola applications private communication. The idea is to build a circuit that is an analog implementation of the Lorenz equations. And Kevin did this as a graduate student working for Alan Oppenheim here at MIT. Kevin, can you tell us a little bit about your circuit and the demonstrations for it?
Sure, Steve. Here is an analog circuit that implements the Lorenz equations. Because of the two nonlinear terms in the Lorenz equations, we have to use two analog multipliers shown here as these brass checks. But all the other circuitry is basically off-the-shelf hardware, operational amplifiers and resistors, and these components basically implement the vector field of the Lorenz equations. And then there are three integrators which take the x dot, y dot, and z dot equations and integrate those variables to actually give us the chaotic x of t, y of t, and z of t of the Lorenz equations. And so all the transmitter implementation is shown here on this 2-inch by 3-inch board. And we also built a second, nearly identical circuit, which functions as a receiver. And the receiver has the property that when we take the chaotic signal x of t from the transmitter and feed it in to the receiver in a special way, that the receiver will precisely synchronize to the transmitter. And so as I go through the demonstration, I'll talk a little bit about the behavior of the transmitter, then I'll show synchronization between the transmitter and receiver, and then I'll show how we can exploit synchronization for certain applications. What we're looking at on the oscilloscope here is a plot of the transmitter variables x of t versus z of t. As you recall, the Lorenz equations have a bifurcation parameter, that's the R parameter, also known as the Rayleigh coefficient. And by varying R, we can actually see qualitative changes in the dynamical behavior of the Lorenz circuit. For example, when I decrease the R parameter, we eventually go to one of the stable fixed points of the Lorenz equations. We can actually listen to the chaotic signals through a loudspeaker, so let me flip that up now. Of course, the R parameter is small enough now, it's on the order of about 20, so the fixed points are stable and we're not really oscillating at this point. What we want to do is increase R until the fixed point goes unstable. And that happens...
Sorry, let me just make one point, which is that he's using non-standard parameter values. So you'll see some weird things here that we didn't talk about, but don't worry about that.
Around R equal to about 33. You can see we're starting to get close because the fixed point goes unstable and we go into a limit cycle regime. And you can actually hear a clear audible tone corresponding to that motion on the limit cycle. If we increase R a little bit further, the limit cycle becomes unstable and actually bifurcates into a 2-cycle. And if we were to look at the signal on a spectrum analyzer, we'd actually see 2 peaks in the power spectrum corresponding to the 2 periodic components of this. As we increase the bifurcation parameter further, we go into a Rosler regime, which is a chaotic regime. And audibly, we can sort of hear that as a very broadband signal. That is, no stable periodic components are involved in when we're in those Rosler regime of operation. And finally, as we increase R further, we get the full chaotic regime. That is where the motion is around the 2 unstable nodes of the Lorenz attractor. Okay, so now that the transmitter is operating chaotically, I want to show you that the receiver is in fact synchronized. And the way we do that is we're going to make a plot of the transmitter's x of t versus the receiver's x of t signal. And if things are perfectly synchronized, we should get a perfect 45-degree line. But of course, because the transmitter's bifurcation parameter is a little bit different than the receiver's, we have some synchronization error. We can actually listen to the synchronization error here. But what we want to do is adjust the transmitter's parameters so that they very nearly match the receiver's parameters. And you can see right now, because the transmitter and receiver parameters are nearly matched, we have a nearly perfect straight line here, 45-degree line, indicating that the transmitter and receiver are operating synchronously. In fact, we can make a plot of the transmitter's y of t versus the receiver's y of t. And again, we see that the y components are synchronized, and we can do the same for the z components as well. So what we have is a chaotic transmitter which has synchronized a nearly identical chaotic receiver. And for applications, this is important because what we'd like to do is take an analog speech signal, for example, add it at a low power to the chaotic drive signal, that is the signal that's synchronizing the receiver. The reason we want it at low power is we want to use the more powerful chaotic signal to mask the speech. And then we want to exploit the synchronization properties of the receiver to actually regenerate the chaotic masking signal, and then we'll subtract it off in analog hardware to actually uncover the message. So let me demonstrate how that works. First, what I'll play for you is the original speech signal coming from a tape recorder. This is the Mariah Carey hit song, Emotions. Okay, now what we want to do is to take this speech signal and actually add it with analog adders to the chaotic drive signal, that's a tape. When we do that, the first thing we see is that there is some synchronization error between the transmitter and receiver. But it's actually a remarkable property of the Lorenz system that the synchronization error turns out to be almost perfectly coherent with the message itself, and that actually helps the message recovery process. Let us now actually hear the transmitted chaotic signal with the music buried in the chaos. Okay, so even though we're actually playing the speech right now, we really can't hear it because it's being masked by the more powerful chaotic drive signal. And so that suggests that a possible application for actually masking information signals with chaotic signals. And what I want to play now is actually exploit the fact that the receiver is very nearly synchronized with the transmitter to actually use that regenerated drive signal in the receiver to subtract it off from the hybrid receive signal. And when we do that, we can actually uncover the speech. Now, the recovered signal is a little bit fuzzy, but we're really not doing much post-processing on it, except for a low-pass filtering operation. Even though it's fuzzy, we can actually understand the words and hear most of the music.
To learn more about what you saw regarding synchronized chaos and private communications, you could first read the paper by Pecora and Carroll, which... All right.
Do you want to ask anything about what you saw? Or heard? Yes? Yes. Right, so the question is, why does it converge to X, only the chaotic part of what you sent, rather than to the whole thing of what you sent, S? And that, you're right, that's the remarkable point. It's somehow because S, which includes Mariah Carey, doesn't make any sense to the Lorenz system. That is, the Lorenz system does what it wants to do, and given that you're driving it with something that is basically X, except slightly contaminated by Mariah Carey, it then does its best to regenerate just the chaotic part, the X. It has no mechanism for reproducing speech or any Mariah Carey song. So, you know, I mean, as you saw, it has a little bit of error signal. There's fuzz on it. So, but still, it's just somehow, I mean, your basic point is right, that the theory behind this, I haven't given you any proof that this will work. And as far as I know, there still isn't any very good theoretical understanding of why it works as well as it does. We did some analysis after this paper of theirs where we gave some arguments, but you know, wasn't very clean, wasn't a simple proof or anything. So I think it's an interesting question, why does the method work as well? Kevin said something in there, you may have missed it, when he said the error signal is itself coherent with the message. So the error signal is not just random junk, it's actually a kind of scaled down version of the message, the song. And so the error itself doesn't really cause as much trouble as you might think. And we had some arguments for that, but still it's not as clean as I would like. All right, well, so I think that is the end of our semester together, except for you taking the test. And so thanks a lot.